The next speaker is Richard Anderson from MathWorks. Richard's a senior developer at MathWorks, been there for 7 years.
Yep.
Working on development for the last 3 years, and I know your background's 10 years in automotive, and a certain period of time working on automatic code generation.
Yep.
And you're working on in-the-loop technology, so hopefully you're going to tell us a bit about what that means.
Yes. Yeah, thank you very much.
That's great. Over to Richard.
Okay, so I'm going to start again. Sorry. Yes, so everyone here again. My name is Richard Anderson from the MathWorks. I'm a senior developer. The MathWorks is a software company that has offices around the world selling to many industries and academia. We develop software that's used for simulation and mathematical analysis. It's been going for 30 years now. This company started in America, and it's used by many industries around the world: aerospace, defense, automotive, energy production, energy transmission, healthcare, finance industry. I mean, the list of industries is pretty long. I came to the MathWorks from 10 years in the automotive industry, where I've been using Simulink and the MathWorks tools to develop embedded software to high integrity standards for going in cars. I joined the MathWorks originally as a consultant, so I would go and visit customers, spend time with them to help them make best use of our tools, and then change their development processes to make use and benefit from the tools that we provided. And then about 3 years ago, I switched over to become a developer. So I moved in-house to help guide and develop the software internally, mainly for an easier life for myself. Less travel, less time in hotels. So I spent 9 months living in the Holiday Inn just down the road from here. So it was that kind of thing that led me to move back into internally. So today I'm going to introduce something we call model-based design. Many companies and many vendors have concepts of model-based design, so I'll talk about our view of model-based design. And as part of that, using that for automatic code generation, and here I'm talking about C, C++, but we also can automatically generate VHDL and code for PLC systems. And then we'll move on to looking at processor in the loop and in the loop testing, which is the area that I actually work in myself. Here we are enabling people to run their simulations, but with part of it running as the generated code on a real system, so they can easily test the behavior in the real world. So first off, a couple of user stories. These are, you'll be able to see these later as well. I'm not going to read through a whole slide, but this one is from across the road, so I thought it was relevant for the locality here at least. The A380, the fuel system on that was developed using our tools, mainly so that they could capture and simulate the system, work out the effect of failures and defects, and really reduce the development life cycle, because the pressures in all industries are to reduce the development cycle of all new products. So they needed ways to reduce that. And they had great success using our tools to do that. The second one's another defense customer. Here they're using code generation as well, but into a certified process. So they had to get assessors in, and it had to be approved for flight. And this was using automatic code generation, and also this second to last point here, using verification on target. And the tools I'm going to talk about later on is this particular use case, so you can test the object code from your desktop. So first, let's go back to looking at how traditional development processes used to work. I saw this in the automotive industry, and then I was quite surprised 10 years later then to see this in other industries still. You start with requirements in your specs, usually vast documents that no one actually reads in full, written in longhand English, often badly written, because often engineers aren't very good at writing things down. And yeah, everyone reads it and comes away with a different idea of what that actually means. You then, from those designs, someone else knocks up a prototype to try and meet those specs. They interpret those specs in some way that maybe what the original person meant, but maybe not. Those prototypes are then given to another team, and they will turn those into production quality code following a very rigorous design coding process. Lots of reviews, lots of checks, and then finally, as the first person was saying, it then gets passed to the testing team, and they have to quickly run all the tests and get it out of the door for the deadline. And often, and this was sort of talked about earlier, these are very different departments, and they just talk. Very, very rarely, they'll just throw a spec over, they'll throw a Word document over the wall, and then the next person has to start from scratch and not have any understanding about what's going on. And it's very, very broken up, and problems happen. So can we improve this workflow? So the first and most important thing of our view of model-based design is, rather than having Word-based documents to capture the system, you have an executable specification, an unambiguous mathematical design of the system that shows how you expect the system to behave. Yes, you have some text because you have to capture the why. Why am I doing this? And also some other criteria. But this executable specification, you start off at a high level, but it can be shared amongst the other teams. It shows the process and how the data flows through the system, and because it's executable, you can see how it behaves from early on and understand its behavior. So you're already testing that it is doing the right thing. And from there, you don't need to make so many prototypes. You can take that and then, with our simulation environment, execute that design, try new things, add in new bits, change some of the parameters in the system, and have faith that what you're seeing out of the other side of that simulation is close to the reality of the system in the end. And you can just keep evolving this design. For the bits that are then going to be deployed, because your model may include some plant modeling to capture the dynamics of the real world that you're interacting with, you can then use automatic code generation tools that will convert your model of the world, your control system, into some C code. And that's all automatic, it's repeatable. You can keep it hardware independent, or you can, if needed for optimization purposes, you can start to add in hardware dependencies so that you can make the best use of the silicon you're using. And because you've got this model that you've been using the whole time, all the way through, you've got this one reference that you're testing and you're running your tests against. And so you're seeing early on what the system is doing. As you make all the changes to make it work in the real world, you're still seeing the behavior of the system and seeing that it works. So with model-based design, you can take your model, you can elaborate it and add more detail of the real world as you go along, and continuously test it, so that you're not just testing at the end with a different team, continually evolving it and understanding how the system works. So obviously that was sort of a descriptive outside, but I work for the MathWorks and we sell products, MATLAB and Simulink, and we would say, and I would say, having been a user before I joined the company, that it is a powerful tool and very flexible for developing real-world systems, multi-domain systems where you've got real plants that mathematically behave like mechanical systems or fluid systems. And MATLAB and Simulink is a means of developing a system and communicating the system to other teams, such that you can reduce risks and develop your systems much faster. And just as an example of that speed up that I've seen, this was a customer I work with, particularly on this one project. Their previous projects used to take about approximately 100 man years. The next one where they used our tools and they engaged with the MathWorks, we got that down to 10 man years. Their first, it took them 2 years to get the first version of code out. It took them 3 months with our tools. But then the real benefit was then how that then fed into their system, such that every design iteration after that was reduced. It was quicker and quicker as they put in more automated testing. So we could then get the design iterations down to 1 release a week. Testing took 8 hours because it was all automated. And then at the end of that, they would also generate their documents and all their reports, so they could show their quality assurance people and that took minutes rather than hours or weeks. So I'm now going to focus on continuous verification. This is and one particular aspect of it. So with this executable specification that I've been talking about, you can keep running different scenarios and data through your system and seeing how the system behaves. We provide some tools that will help you do this and allow you to tackle it in different ways. We have some static analysis tools for both analysing the model at the top, but also the generated code that it comes out the other side. We've got some tools that will help you meet standards, work towards the requirements of different certification authorities, and also some industry standards that have now come up for modelling with our tools. And then we've got dynamic verification. Here I'm talking about simulating the system at different stages, seeing how it behaves, seeing as you change it what happens and whether it still behaves the right way. Seeing as when you add the constraints of the real world, you're not just working on a 64-bit machine on your desk with 48 gigabytes of RAM. No, it works perfectly and it operates really, really quickly. But then you've got to try and put it on an 8-bit micro in a car, which has got 6K of memory. Does it still work? Does your system actually still work? So we can examine the behavior of a system using complex closed-loop control plant models. So these can be mathematically based or based on models of real-world components. You can also you've captured input data from the field, from real vehicles, real systems. Or you can design specific test cases to test particular parts of your system. But then we also have some tools for automatically generating test cases. One to demonstrate particular properties that you've embedded in your system. If these things happen, this thing can't happen. Prove to me mathematically that that's the case. Or if you're trying to meet particular coverage metrics, we have tools that will try and fill in the holes where your manual testing and your design testing hasn't quite met 100% coverage, and it will come up with test cases to meet those other points, or tell you if there is dead code in your system that you just can't get to, which may have a good reason for being there because it's defensive, but also may show that you've got some system that's unaccessible, that shouldn't be there and should be deleted. And then we'll move on to the area that I work in the loop testing. This is taking all of these concepts, run nicely in the desktop, and then starting to use those against the compiled generated code. We've got software in the loop, which is running these tests on your desktop against the generated code, compiled for the host, so not your real environment, but then also process in the loop testing, where you're running on the real silicon that you're ultimately going to put in the car, the aeroplane, using the correct tool chain. And so you can see the effects of the tool chain, how the compiler has interpreted the C code, and is it still working. And also you can see the effect of using particular optimizations that you want to make use of for your hardware. So this picture, I'm not going to go through all of it, but in this first bit, the simulation I'm talking about is verifying that the original model meets the requirements and does exactly what you think it should do. And then the software in the loop testing is checking that the source code meets the behavior of the model, but in a simple environment on your host computer. And then processing a loop, it's a step further, it's a bit harder, but it's running on your real hardware, the real object code, so you can verify that that's behaving correctly. So how do we do software in the loop? This is sort of going into a bit more of the guts just to explain how the system works. So here's a Simulink model. Possibly some of you have not seen it. We've got a flow diagram of inputs on the left coming into the My algorithm, which is your controller. You've got some plant model that reacts to the inputs from your controller, and then you've got some verification, and you've got some feedback here as well. So this simulation will run for a certain amount of time and look at the behavior of your algorithm against your mathematical plant model. The Simulink tools that we sell, when you generate code from your system, you get the object code compiled with the host compiler or the target compiler. We then automatically wrap around that a test harness with a test application that will get launched automatically either on your host computer, your laptop or your desktop computer, or downloaded and launched on your production hardware. And through some communications channel, we'll then communicate back with Simulink so you can run your tests on the real hardware. So here, for software in the loop, we're using TCP/IP communication between two processes on your host computer, talking to each other. It's not real-time processing, so you can't interact with the real world in this testing environment. So it's not the same as Hill testing, but it allows you to have a synchronized simulation, so you can fake the real world for your generated code, and so you can see how it behaves. And from this, you can understand the numerical behavior of your system. You can have some understanding of the execution time and how that's going to behave in the real world, although because you're not running on the right hardware, that might not be, that is not the final assessment. You can use this to collect code coverage, and this is often accepted by certification authorities, that you can collect code coverage running a set of tests on your host computer, and then if you rerun those same tests on your target computer, they will accept that you've got the coverage, even if you can't measure the coverage on your target computer. And you can create some certification artifacts from this process. And the beauty of this is that anybody who's got embedded coder or their desktop can use this. They don't need any extra tools, any extra software. They can just do this testing at their computer. So the developer who's developing the system in the first place can do this level of testing. For processing the loop, it's the same idea, except this is a bit more complicated because you have to tell it how. You have to have some real hardware to connect up to. But here you can have much greater confidence that you're testing and understanding the exact numerical behavior on the target, getting real execution time metrics and coverage metrics if you've got the tools, and certification artifacts. Here you do need to supply some extra information, and I'll look at how to do that in a second. So the key benefits of Simulink are it's working in a controlled and easy environment at your desktop for all this testing. For SIL, you don't need anything extra. You can do the testing there, and it allows you to easily debug what's going wrong when things aren't behaving as you expect. You can verify the correct execution of the behavior of your compiled code. You can collect metrics. So we have integrations with two code coverage tools, Bullseye and LDRA testbed, so that you can use those third-party tools to gather code metrics from your testing cases, and also you can measure execution time. And as I said, you can evaluate the effect of specific hardware optimizations, whether it's using particular libraries that your hardware vendor supplies, or making use of different features of the compiler, and generate artifacts. So you can move your verification earlier and detect errors much earlier in the life cycle, hopefully reducing the cost of your system. Oops. Just a quick look at execution profiling, how we do that. So for any function in the system, we will automatically insert some probes around that call to that function, capture the data as your test cases are running, and then return that to you and show you a report back after your simulation has run as a means of capturing the real time that the system took to run. And because we're running non-real time locked step with Simulink, for that one time step, you are measuring the real execution of the system. So this only works for single-threaded applications at the moment. We support, as downloadable artifacts, integrations with many pieces of hardware. So ARM boards, this is an STM Micro discovery board, which has got an ARM Cortex-M chip on it. I can plug that into my laptop and download all the tools from within MATLAB to connect up to that from Simulink. So we have an ever-growing list of target support packages, but we can't support every possible combination of hardware, compiler, debugger, and communications channel. So we also provide an API to allow you to extend to your particular hardware. So the purple boxes are things that you would need to supply to make this work, but it's a published API that's been stable across many releases, such that you can plug into any hardware on your network, and it's not much work to do this, especially if you've already got the communications channel available between your host computer and your target computer. And actually, you can go a step further, and often we've seen this with several customers now. You can plug in many pieces of hardware onto your corporate network because you're just using TCP/IP to connect to them, so anybody at their desk can run processing the loop tests against different pieces of hardware that they're using in their project. Someone else can maintain the actual hardware and that's plugged in, but you can have all of these targets available on your network internally to your building, such that the developers, whatever project they're working on that day, can connect up to that hardware and run their tests. So the takeaways I'm hoping you've got some from my talk are that model-based design allows an easier collaboration between the different teams, brings cost savings. So I've seen real cost savings with both in my career and also working with other customers, helping to spot problems a lot earlier, so you're not finding them right at the end of the release. And the executable specification is a lot easier to understand and share between teams and companies. In big supply chains, you see now customers, or the OEM, for example, requiring that their supplier provides a Simulink model for their component that they are selling them, so that they can include it into a large model, and so they can understand the behavior of the full system. And processing the loop testing, this promotes early and easy access to testing on the hardware, such that you can understand quickly that the design decisions you're making do work and do make sense when you run it in the real world. Allow you to gather metrics and to easily reuse test cases in your production environment. So as you're working, coming up with ideas about how a system should work, you can then try those systems again, those tests again in the real hardware. And that's it. So if you've got any questions, that was quick.
Yeah, can you, because we recorded it.
Yeah, so you mentioned something which was bugging me since you said it. I just want to make sure if I understand this correctly. As far as I understand, what you're saying is that when you generate the code and you generate the object you use for testing, you're deploying the object, the code that I've generated, plus a test harness around that, and that's deployed to the hardware.
Yes.
So basically, if in a safe industry, if you want to claim, your testing and you want to say that the software is safe, that would imply that I still have to take the object I've compiled or the code I've compiled without your test harness, also run it on the hardware and run the same test, or a separate set of tests I've created to get proper test coverage.
I think you can use that testing environment as evidence that you've done the testing. And the way our code generator works, it generates the code for your application first, and if you then and then do test, and then you do processing the loop, it will use the code that was generated and it won't regenerate it. So it will be the exact C files that you tested that were running in processing the loop.
But it will also include the test harness.
It will, yeah, it does include the test harness.
So when I deploy it onto into a real aircraft,
yeah,
I either have to deploy it with the test harness, or I have to remove the test harness, which means I've changed the system I was testing. That's just a curiosity.
So yeah. Maybe we should talk later. I'm not quite sure I understand exactly the question, but yes, our test harness isn't for deployed in the final system, and it isn't all of the testing you will need to do with the final system, but it is accepted by certification authorities that is a valid part of testing that component in your system.
Yeah.
Yeah.
Yeah, so provided you do additional things to compensate for the fact that you're removing the test harness, I'm assuming. That's it. That's it.
Right, thank you. Any more questions?
Yes, perhaps I can give you a hand for that one. Our customers call this hardware in the loop, which is the next cycle after the process in the loop, where you have tested your software in with the test harness. That gives you an idea that your unit tests are correct. And then when you take only the functional aspects and you put it together in a big application, then you have to do additional tests for like high-level system-level tests. But of course, on the final deploy system, you don't put the test harness. You use the test harness only to drive your unit tests, basically. Okay. I just wanted to make a couple of comments and questions, a couple of things that perhaps will generate a bit of debate. We do tools for structural code coverage. Yep. Yeah. MathWorks is also on the list of tools that you can use for code coverage.
Yes.
And we've seen more and more pressure from certification authorities, especially in the DO17AB, to move to on-target testing, because the leap of faith that you have to do from claiming source code or even code coverage on a host from what can happen on the target is becoming so big that there are, let's say, a few sweaty palms that, yes, it should work in theory, however, you don't know what you don't know. Yep. And therefore there is value of being able to do that on the host, which I think is good, to make sure that you have a very quick turnaround to check that your tests are right. Yep. But in the end, it saves effort and headaches on the certification part to be able to claim all your trouble analysis, code coverage on something which is as close as possible to the final system. That means full build, compiler options, and their target as more representative as possible.
Yes, so our process in the loop, it does support on-target code coverage. So LDRA testbed, one of the things we support out of the box, supports on-target, and we support that for PIL, and we have worked with other suppliers of code coverage tools who have on-target testing tools and have helped them extend process in the loop to use their tools on target to get to meet that exact requirement.
I may have another comment, but I'll.
Okay. Any further questions?
One there.
Hello?
probably a quicker question. So you keep talking about object code and things like that. Is it a qualified code generator?
No, it isn't.
Okay.
We provide tools to automate code reviews and add traceability, such that you still need to do some hand code reviews, so some reviews of the generated code to make up for the fact that it's not a qualified code generator, but it isn't a qualified code generator. But we have tools to reduce the amount of manual code reviews that you have to do.
So I guess it produces code and then you run it through RDRA, will instrument it and do the static and dynamic analysis.
That's one of the tools that you can do. Yeah. But we also have our own tools for demonstrating traceability and correctness of the generated code to help meet those qualification needs.
Okay. Well, WCET, does any of the tool chains support the worst case execution for 178?